Thank you very much. I'm going to talk about the reinforcement learning and the basal ganglia. So I always wonder what is the killer application for neuromorphic chips. So these days, as you know, many special purpose processors has been developed. And I think they are categorized in one of three things. The first category is, of course, deep neural network accelerator. That chip processes compute tensor calculations that accelerates tensor calculations. And their killer app is, of course, deep learning. The second category is something like we call annealing chips. The annealing chips compute simulated annealing, and the killer app is, of course, combinatorial optimization problems. And the third category is our neuromorphic chips. The neuromorphic chips can build and simulate spiking neural network. And the spiking neural network can do anything. For example, a spiking neural network can simulate deep neural network, can solve combinatorial optimization problems, can simulate reservoir computing, associative memory, raster optimization. So anything can be done by spiking neural network. However, these applications can be done by other technologies as well. So I think the killer app is something that can be done only by neuromorphic processors. So what is the killer app for neuromorphic chip? So in my opinion, reinforcement learning is a killer app, can be a killer app for neuromorphic chips. Specifically, online on-chip low-power reinforcement learning can be done only by neuromorphic chips. So I think this is a target. This is our target application. And reinforcement learning is mediated by the basal ganglia in the brain. And the basal ganglia had some quite difficult, anatomical structure. It's composed of about 9 neuronal layers. And we implemented this circuit, and based on the anatomical structure, and we employed 900 spike response model neurons to build for this network model. And the learning is more important for basal ganglia model. And we employed spike-based temporal difference long-term potentiation rule, which is basically developed by Fremod's paper in 2013. And we employed this synaptic learning rule for corticostriatal synaptic inputs. And then everything was implemented on using C++ and CUDA. And we used explicit Euler method to solve the differential equation with temporal resolution of 1 millisecond. And thanks to the GPU, the parallel computing capability of the GPU, we succeeded to simulate the network dynamics in real time. Well, real time means that the computer simulation of the network dynamics for 1 second, complete within 1 second with the real world time. Actually, our model calculates the neural activity for 1 second within 0.61 seconds, so slightly faster than real time. And this property allows us to perform reinforcement learning online, which means that learning proceeds simultaneously during the behavior. That's a very important point. And I'm going to show you some examples. The first example is standard water maze task. This is a maze, and this blue circle represents a goal, and the red square represents the obstacle. And initially, the agent is put one of the 4 starting points, and the agent has to find the goal. And when the agent finds the goal, some positive reward is given to the agent. On the other hand, when the agent hits at the obstacle, the agent receives a punishment or a negative reward. It's a very simple task. And simulation works something like this. So before learning, the agent just crawls in the maze because the agent doesn't know where the goal is. So the agent just go back and forth and sometimes hit the obstacle. And the right figure shows the raster plot of the spiking neurons in the basal ganglia. And horizontal axis represents time, and the vertical axis represents the neuron number. On the other hand, after learning, the agent goes to the target almost straightforwardly while avoiding the obstacle. And this is, again, the raster plot of the neuronal spike patterns. This is some summary picture. And the left figure shows the trajectories across 100 trials. And trial by trial, the agent tends to succeed to find the goal. And right figure shows the elapsed time for the agent to reach to the goal. And during the trial by trial, the elapsed time gradually decreases. So the agent learns to reach to the goal more quickly by the learning. So this is one result. And another example is a reaching task. So in this task, the target is given at one of 8 positions, and the agent has to move the two-link arm to the target. If the reaching succeeds, the agent receives a positive reward, and if fails, nothing is given to the agent. And in this simulation, for the first 500 trials, the target always appears at the top. And for the next 500 trials, target appears to always right, to always left. And this is the result. In this case, I just show only the trajectory of the arm. And for the first 100 trials, the target always appears here. So agent learns to reach the arm to this area. And after the 100 trials, the target position changes from here to here, and the agent relearns to move the arm to the next target. And they are, again, raster plot of the spiking activity of the basal ganglia model. So this result shows that even if the target position changes during the learning, the agent continuously learn the correct target position. So it's very nice. Okay. And a summary. So we succeeded to build a spiking network model of the basal ganglia using a GPU. And the model can perform reinforcement learning, and actually online reinforcement learning, because the computer simulation is real-time simulation. And actually, we have a poster, so we have some questions. So please just drop me a line at the poster session. Thank you very much.
Okay, do we have a question? I see a hand.
So in the hand-reaching task, does it take shorter to learn how to reach the second point? Like, does it have some memory of the learning?
Good question. There is no saving property. The same time is necessary for the second target. So there is no acceleration.
Okay, thank you very much,
Thank you.
Tadashi. And